Few important points to remember. Always feed your scalar using your training data and then use it to transform both your training dataset and test datasets. Do not use different scalars on your training and test datasets. This could skew your data. Do not use test data to feed your scalar. This could lead to what is called as data leakage. It means your test data set would no longer be a holdout data set, meaning your model has already seen the test data set. So it wouldn't be a new data to it. All right, let's go back to coding. So we previously applied a linear regression model on our diabetes problem from the Scikit-Learn datasets, diabetes. It turns out that there is a gap between the accuracy rate on the training dataset and on the testing datasets, which is an indication because the accuracy on the training dataset is higher, much higher than the testing dataset. This is an indication that we have overfitting problem. Last time, to overcome this problem and resolve it, the overfitting problem, we tried to use regularization. We developed a region, a Lasso regression, and it turned out that actually the gap is improved, but still the gap is noticeable. Now we want to use feature engineering, feature scaling, and later on polynomial features to see if we can improve the performance of the algorithm on the testing datasets and overcome the overfitting problem that we have here. So before we start, you need to actually run the whole code so that it is updated. So you can go to cell and then run all. And it's going to run all the commands that we have and then come back to the feature scaling normalization. All right, so now we want to apply the MinMax scalar to normalize our data. And then we're going to apply a ridge regression on the scale data. So let's import the MinMax scalar from the Scikit-Learn pre-processing module from the Scikit-Learn. Notice that M in MinMax and S in a scalar are capital. All right, so let's now define a copy object of this, and I'm going to call it a scalar, my scalar or scalar. So that's a copy of MinMax scalar. All right, so now I want to use this scalar to normalize our data. So I'm going to fit the scalar into our training data set, the feature variable. So a scalar fits into only the feature variable, xtrain. Right. Now I can, after that it is trained, I can transform the trained data using the MinMax scalar and normalize them. And then I'm going to keep it to a new feature variable name. So I'm going to call the feature variable names as xtrain scaled. And then I'm going to use the scalar that is now fit, and then call the transform function on the xtrained, the feature variables. Train. So this is going to scale the xtrained, the feature variables, and then put the scaled feature variables to a new data set here, xtrain is scale. Right. So we do not scale the target variable, only the feature variable. All right, so now we can use the scalar to transform our test data. Never actually fit the scalar on the test data. So we fit the scalar on the training data, then transform our X-train values, feature values, and then transform our X-test values. So I'm going to call this X-test scaled, and that's going to use the scalar transform, and then I'm going to give it the X-test variables. Again, we do not transform the target value. We do not scale the target variables. We could actually combine this fit and transform these two lines into just one line here. So that would be, I would have to say X train scaled. Actually, the function is here. So we could use this function, X train scaled. It's scalar. The command is fit underscore transform. So this would actually both fit first and then transform. And it's going, you can replace it with these two instead of this. Right, now that we scale our data using the MinMax scalar, we're gonna reapply the regularized regression model, the ridge regression on the scaled data. So let's define and feed a ridge regression on the scaled data. So I'm gonna call it my ridge. That's going to be a ridge with specifying alpha the parameters, the penalty coefficient here. I'm going to set it as 45%. We previously also set it as 45%. If you go back here, 45% alpha. So we do the same here, 45%. We can play around with it to see what value would fit better. So let's also fit our model or train our model on the training data set on the scaled train. So X train scaled. X train scaled. I'm gonna make sure that I use the proper spelling. And then also Y train. So since we don't scale the target variable, so that's it. We're gonna just use the Y train. Right. And now that our algorithm is trained, we can make prediction. So Y predict. I'm gonna ask my ridge to make a prediction on the X test scale. Right. So let's now print out the R2 score for the actual value Y test and Y predict here. So that's about 32%, which is pretty low. So we can play around with different values of alpha to get better tuning or optimizing the parameters here. So let's go back here and increase this, for example, to 1. See what's going to happen. It improved a little bit. I'm going to increase it to 2. Improved. I'm going to increase it to 4, double it. Improved. I'm going to increase it to 6. Improved. I'm going to increase it to 7. All right. How about 8? It decreased. 9. It decreased. So I'm going to keep it at 7. All right. 36. So let's now add the R2 score of our ridge scaled algorithm to the R scores table. I'm gonna call it ridge scaled. So before we do that, we need to also do that, apply it on the training dataset, make prediction on training dataset. So let's do that. Y predict train on the X train scaled. R2 score for Y train and Y predict train. Okay, so now I'm gonna copy this here and then copy this here. Okay, I'm gonna get rid of this. So let's print out our two squares. Right, it looks like that we have been able to improve the accuracy of the ridge regression on the test data set. So if you look at here for previously, the accuracy score for the test data set was about 30.357 and now is 0.362. For the training data set, it's almost the same. It's a little bit improved, but so the gap actually is getting smaller and smaller. Next, we want to apply a lasso regression on the scale data. So let's do that. I'm gonna name the new lasso, my lasso, and that's going to be a lasso. And the alpha parameter, I'm going to use the same alpha that we used previously. So previously we used actually 17% as alpha. So I'm going to use 7% now. We can play around with it and make a more optimized value, find an optimized value. So let's also train our data in the same line. I'm going to give it the training data set, and we have to use the scaled value and the Y train. So as you see here, we do not scale the target variable. So let's now make a prediction on the test data set. We're going to use the scale data. So let's print out the R2 score for our prediction. So we do not scale our target variable Y. So that's why you don't see scale data used here. So it's about 33%. So let's change these values. I'm going to go a little bit higher. So for example, 30%. Let's run this 33.8. I'm going to go higher 5, 33. So it's improved. Higher 6. Higher. Higher. It improved. Alright, let's go higher. Okay. Can go to 1. Alright, so it's gonna get worse. Alright, so I'm gonna go with 0.9. Okay. Alright, so now we have our lasso on the scaled data. Let's add it to the R scores table. So let's do that. So first, let's make a prediction also on the training data set. So I'm gonna call by predict train. Then print out the R2 score. Right, so let's now add it to the R2 score table. scores. I'm gonna call it Lasso scale. Then I'm gonna add this. Okay, so let's print out our scores. All right. The gap for Lasso for the test is a little bit improved, just a little bit. So using the scaling data or normalizing data, we were able to uh, make the gap between the training and test accuracy scores smaller. Now we want to use polynomial features. The reason for that is if there is a nonlinear relationship between our data, between our variables, then a linear relationship is incapable of capturing that relationship. So what we're going to do is we're going to generate new features, polynomial features, and then apply a regression model on those features. So let's do that. To do that, we need to first generate polynomial features. So I'm going to import the polynomial features from the Scikit-Learn pre-processing. And here I'm going to create a copy of that object, and I'm going to call it poly, for example. That's going to be a copy of I'm going to use degree 2. You can use higher degrees, but you need to know that higher degrees is going to generate more features, and it's going to probably blow up your data. So you have to be careful, but you can play around with this. Okay, so now that we have our function, the polynomial features function, we can generate new features. I'm gonna only the feature variable. So I'm gonna call this xpoly, and then I'm gonna call my model and my function, the polynomial function, and then fit transform my previous data, because the x features are in the diabetes 8. So this includes our x variables or features. So this is going to create new polynomial features, and it's going to put it in the xpoly. It should be transform. Right. Now the next step is to split our data. So let's do that. And I'm going to give the x poly now here. Y is not going to, the target variable is not going to change, so I'm going to use the target variable. The target variable in the diabetes is in the diabetes target. Diabetes. Make sure that you do the spelling right, otherwise you're going to get error. So the test size that I want to use here is 20%. By default is 25%. And we're going to use the random state to make sure that all of us get the same output. Now that we have splitted our data, let's go on and go ahead and apply a ridge regression. We're going to use a regularized regression because we already have a lot of features. We created new features. So regularization is going to help because otherwise we're going to have kind of complex model. So I'm going to call my model myReg. I'm going to use alpha equal to 40%. You can play around with this, of course, and to tune the parameters alpha. So let's also tune our or train our algorithm in the same line using the fit function on the training dataset. So this training dataset is already including the polynomial features. So now we can actually make a prediction. Let's compute the R2 score. It's about 0.358. Okay, so let's also compute the R squared for training and then save it to the R squares table. Let's see what is the R2 score. It's about 50.523. And let's then add this to the table that we built. R squares. I'm gonna call this polynomial 2 ridge regression. So poly 2 ridge. Then I'm going to give it the R square values for training. First, you have to put the training because this is how we design the index for, and then the testing. So let's print out the R squares now. So this is the last column. We have the degree 2 polynomial ridge regression. Here's a little assignment that you can do. So we did the 2-degree polynomial ridge regression on our data. Now you can apply a 2-degree polynomial lasso regression on dataset. You can actually also play with the degree, go with 3 or 4 and see what would happen. Tune the alpha, the parameter, the coefficient of penalty coefficient to find the best one. And then compute and add the R squares values, the R2 score for training and test dataset into your R squares table. All right, so we applied a ridge regression model on the polynomial features added to our data, degree 2. So now I want to scale the polynomial features, and after that, apply the ridge regression. If you remember, we applied a scaling, MinMax scalar here. So we apply the MinMax scalar using the scale function. So let's do that. Let's scale our data or normalize our polynomial features first, and then after that apply the ridge regression. So X train scaled. I'm going to use my scalar to fit and transform my X train. So what this does is, first of all, we're only going to scale our feature variable. We're never going to apply that on the target variable. And second of all, we're going to fit the scalar on the training dataset, and we're going to transform the training dataset and the testing dataset. So we never fit the scalar on the test dataset. So let's now transform the test dataset. All right. Now I'm going to apply the ridge regression. So I'm going to call another ridge regression model. You can play around with the parameters alpha here, the penalty coefficient, to find the best and optimal value for it. So right now I'm going to go with 20. This is the value I previously have found here. All right. We could also actually fit the model to our training data set, the same line here. So I'm going to use the X-train scaled, the scaled one, and Y-train. We never scale or change the normalize the target variable, so that's why it doesn't have a scale here. Now we can make a prediction using the trained ridge model that we have made. Okay, so I'm going to call it Y-predict, and then I'm going to call my model to make a prediction on the test data. It's scaled. Yeah, just like this. So let's see the R2 score now. For Y test and Y predict, it's about 0.337. You can also do that for training. It's scaled. And find the R2 score. All right, that's actually pretty good. It's about 48%. It calmed down. It came down. The gap actually is now reduced. So let's now add this to the R squares table. So I'm gonna call the R squares for. I'm gonna call this model the Poly2 ridge scale. And then I'm gonna add the training R2 score should come first, and after that the test. So let's call the R squares now table. So it added here. As you see here, the gap actually is also now it's reduced.